In this lecture, I'm going to talk about the properties of Laplacian transform. So in the previous lecture, I talked about the basic control analysis approach. First one is by solving the ODE. The second approach is by using the Laplace transform and the inverse Laplace transform. So in the next couple of lectures, I'll talk about the property, how do we compute the Laplace transform, the properties of Laplace transform, and the inverse Laplace transform. Okay, so let's go review a little bit about the definition of Laplace transform. So Laplace transform is given by, for a function ft, is given by integration from 0 to infinity e to the minus st times ft over dt. So that's integration of the original function ft times e to the minus st and over for t over 0 to infinity. So that's sort of the definition of the Laplace transform. Okay, based on this basic definition, we have a couple of properties that I mentioned first here. The first property is called linear property. What the linear property says, if I have two functions, x1t, x2t, okay, and the Laplace transform for the x1t, x2t are the capital X1t and the capital X1s, and the capital X2s. So then the Laplace transform of x1t plus x2t will be just the capital X1s plus capital X2s. Okay, that's quite intuitive. It's like the sum of two functions will have its linear Laplace transform given by the sum of their corresponding Laplace transform. Okay, that's sort of what the linear property says. So to analyze why that's the case, so I can just use the definition. If I plug in the Laplace transform definition, it's nothing but I have just copy this function over here, and that time e minus st, then integrate the product for t over 0 to infinity. So that's the definition. We can use the property. I can split this to x1t and x2t by having their product with est respectively, and just separate them. So this is the same as the previous one, that separate the product. So this one can be written as e minus t times x1t plus est minus t times x2t. So we just have to separate them. And each one, this is just definition, right? Because this is according to the definition over here. So x1t times e minus t, and integrate that product from 0 to infinity. That's just the Laplace transform of x1t, which is x1s. Similarly, the integration from 0 to infinity of e minus st times x2t over t is just x2s. That's the definition of the Laplace transform. Okay. For example, if I give a function which is ft is given by 1 plus t for t is greater than or equal to 0, and for ft will be 0 for t when t is less than 0. So if I use the definition, so of course right hand, this is a plot of what ft looks like. So you have basically to the left of the imaginary axis you get a 0. On the right hand side you get on the right hand when t is starting from 0 is 1, then it linearly grows. Okay. So by using the definition of the Laplace transform, it's just fs, which is integration from 0 to infinity e minus st ft. So now I can sort of write this one as, I can rewrite this one as f1t and f2t. Let's write it differently. So f1t is just equal to t when t is greater than or equal to 0, and 0, which is t less than 0, and f2t is 1, 0. This is t greater than or equal to 0. This is t less than or equal to 0. So if we do this two forms, you can see ft is just equal to f1t plus f2t. That's fairly easy to find out. So naturally, if I do this one f1 and f2t, so it's just according to linear property. So the Laplace transform of f1t plus f2t is just the Laplace transform of individual one. Okay, individual one is just this guy and this guy. Okay, so this Laplace transform, so we talk about how to compute that. We can use the definition to compute it. So for I guess it switch this to, okay, because f1t is Laplace transform for t is 1 over s squared. For the 1 is just 1 over s. Okay, so the reason we have this nice property because there is a table. Okay, you can check Laplace transform table. So the table will give you some basic function and its Laplace transform. For example, you can tell one Laplace transform is just 1 over s, and t Laplace transform will be 1 over squared, so on and so forth. You can find the tables. You don't have to do this computation directly. You just have to split your function into some existing form. Okay, so then you can just use a table and use a linear property, and you're done. So this is the first property. The second property is called homogeneity property. So what it says is you can scale. If I scale the function by a constant scalar a, then the Laplace transform is also scaled by the same number. Okay. Well, a, of course, a should be a constant. Okay. For example, here, if I have ft is twice of t for t is greater than 0, and ft less, it is 0 when it's less than or equal to 0. So apparently this one is, I should say this. If I say define f1t is t greater than or equal to 0, and 0, which is t1t is less than 0. So this is, we can say ft is twice of f1t. So the Laplace transform for ft, so this is, I just ignore, this is L ft, Laplace transform is given by, notation wise, given by fs. It's twice of Laplace transform of f1t. So apparently for the f1t, according to the property, this f1t is just t, right? You can also look at the table over here. So it's 1 over s squared. So it's twice, 2 times 1 over s squared, which is 2 divided by s squared. That's its Laplace transform. Okay. You can also combine the two properties. For example, if I have ft is 2t plus 1, t is greater than or equal to 0, and 0, and t less than or equal to 0. So the Laplace transform of this ft, you can see is Laplace transform of, I can just write down this one. I don't have to define all the functions. This is 2t, okay, plus Laplace transform of 1. Okay, Laplace transform 2t is 2 Laplace of t plus Laplace of 1 is 1 over s, according to the table over here. Laplace of t is 1 over squared, so this is 2 over s squared plus 1 over s. You can even combine different properties. Okay, so this is the second property. The third property is called a shift property, which means you shift your signal to the left and right by a certain value. Okay, so when people say shift, it doesn't mean it's a shift up and down. You can also shift up and down, but shift up and down is just plus. For example, if I shift the signal here, this is my original signal. It's just let's say this is my whatever signal I have. Okay, if I shift it up, okay, if I shift up, okay, it just means, for example, originally it's like this. If I shift up to this value, it's just use plus. It's the same as the original function plus the difference. Let's say the difference here is 1. So, and the function here, let's say this is f1t. Now this shift up you get here is f1t plus 1. So it's just summation. Okay, so you can apply the linear property to solve it, right? Once here, I mean is you shifted the function to the right, left and right. Okay, this is different. So apparently the shift, what's the relation between the original function and shift function? The relation is given by this. Assume here I shift by some t. Okay, I don't know what the value is. It's a t value general. Shift to the right. Okay. Now the function is just be given by f1 t minus t. Okay. The reason here is why it's minus not plus is, let's say here, this is a value when it's at 0, okay, over here. My ft value, say here is 1, okay. Now what value will start to get a 1? So only when, according to over here, only when t, your little, the t is equal to big T, you become, this become, because when it's equal, this is equal, you get a 0 over here. Because here your 0 is, f1 0 is 1 over here, so this become 1. Less than you always 0, right? Which means you should be here. Less than t is always 0. Greater than or equal to t is always 1. That's why it's moved to the shift to the right. So similarly, if I do have another case, let's draw over here. If I draw another case, so if I shift to the left, let's say I'm shifting to the left, and also the shift is given by t. So now, what function do I get? So the function will be f1 t plus t, as you can imagine. So it's a plus. Okay. So the shift property says, okay, here just talk about what does the shift mean. Okay, don't get confused about a positive sign or negative sign over here. So the shift property says the Laplace transform of f t minus t. Okay, this is minus. Remember, here is a minus t. Here this minus is e minus tau s times fs. Okay, which means it's the Laplace of the original function without shifting time e minus tau s. Okay, this tau is how much shift we have. So this is actually the same value. The shift will goes here. It's the same value over here. Okay. Of course, if I have L f t plus tau, you shift to the left, it will be e tau s fs. Okay. That's a shift property. The next one is convolution property. Okay. Convolution property talking about for two functions. Okay. For two functions, let's say f1t and f2t. The convolution is given by integration from 0 to t f1 t minus tau f2 tau d tau. So that's the convolution. Okay, I don't want to talk too much detail about what does convolution mean. So you can check it out what convolution means. Okay, so for convolution, the Laplace transform of convolution is given by f1s times f2s. It's pretty simple. Okay, it's just f1 and s times fs. So this f1s will be just the Laplace transform of f1t, and f2s will be the Laplace transform of f2t. Okay. So this is a little bit hard to understand. Okay, so I'm going to provide a video to describe, to show why this Laplace transform of a convolution is indeed the product of two the transfer function of two individual functions. Okay, it's a little bit harder, and I'll show you why that's the case. Okay. The next property is called integration property. The integration property says the Laplace transform for the integration of 0 and t f tau d tau is fs over s. Okay, again here fs over here, it is the Laplace transform of original function ft. Okay, so let me repeat. Let's emphasize here. So this one is says over here. This is different. F integration 0 to t f tau d tau. This is not equal to Laplace transform of integration 0 to infinity or whatever value f tau d tau. Okay, the reason is this guy is a function of t. This is a function of t. Because for different t, you get different value, right? This one is a constant, basically. Assuming that the integration exists, of course. This is a constant, okay? So because this guy, what is the Laplace transform of constant? I can do this one. This is the same as Laplace transform of I can move the constant outside. It's 0 to infinity ft d tau according to the homogeneity property, which is time L1. Okay, right? What is Laplace transform of 1? So according to the table, it's 1 over s, right? So this becomes, let me go here. So this is 1 over s times integration of 0 to infinity f tau. This should be f tau d tau. Okay, so this one is easy to do because I can use the homogeneity property to figure out what is the final value. This one is difficult. According to integration property, integration must from 0 to t, okay? It cannot become from 0 to infinity, okay? This one is given by fs over s. Why that's the case? Okay, let's take a look at why that's the case. So of course I have to use a definition. I cannot use a previous property to figure out this one. So let's use a definition. So the Laplace transform for any function is given by that function times e minus st and integration over dt from 0 to infinity. That's what the definition means. Okay, now let's take a look at what we do. Okay, now I'm going to move this one to the right hand side of dt. So which means I want to have d to the e minus t. Of course, this will be different from previous one. I have to add on this one minus 1 over s. That's because d e minus st is use a chain rule. It is minus s times d minus time e minus t times dt, right? So if you place this one, if I just have this term, if I plug it back in, you see it's different from this one. There's a 1 minus s over here, extra minus s over here. So I have to add an extra 1 that can cancel this term. Okay, that's why we have this. So let's delete this. So then let's use the integration by part. So this one is we keep this 1 minus 1 over s, and then this we do integration by part. So this is just this part times this guy. Right hand side is this guy times this guy. Integrate from 0 to infinity for t from 0 to infinity. Evaluate t at t is 0 and t is infinity. Minus, I just swap this 2. So I have integration from 0 to infinity e minus t times d of this guy. Okay, look at this guy. So d integration 0 to t f tau d tau. This guy is just equal to ft. Okay? The reason is the integration for this one, if I draw a picture of it, okay, if I draw a picture of ft, this is my ft, for example. So integration f tau, for example, the integration of this one is the area of this. Let's say this is the area. This is the value of integration of this part, right? So this is my tau. So as the two move back and forth, so you want to check how this derivative, this means how fast this guy is changing, basically, right? Because it depends on how big this value is. How this red one represents f tau. Okay, so it really depends on how big this f tau value is. That's why this is ft times dt. So that's what this means. Okay, what's the computation of d integration 0 to t f tau d tau. Okay, you can also do this one because this one actually means the integration t f tau d tau over dt. This is just ft, so that's what it means. Then we can come up with this. Okay, so when we replace this guy by ft dt, of course let's compute this one. So for this one, when you evaluate t is 0 over here, the integrate this guy, you integrate from 0 to 0, this guy becomes 0. It doesn't matter what this value is, right? It's still 0. When t goes to the infinity, now this guy is going to be a little bit complicated. Okay, so when you have this one, okay, so remember here, you remember s is positive in my original, in my previous lecture, if you don't remember that. So let's compute this value when t is going to infinity. Okay, so this becomes 0t f tau d tau times e minus st, okay, which is, I can put it as a denominator, which is 0 to t f tau d tau over est, right? Okay, so that could be two different cases. One is this guy goes to infinity as t goes to infinity. Remember here t will go to infinity, right? So this guy goes to infinity as t go to infinity. Okay, this is one case. Second case is this is does not go to infinity. This is a finite number. So and divide by, because this guy will go to infinity, right? So this will be if, let's go two cases. So this guy will equal to 0 if integrating from 0 to t f tau d tau does not go to infinity, okay, as t go to infinity. Okay, what if it does go to infinity? Oh, I should put a limit t go to infinity, limit t go to infinity. So what if it does not go to it does go to infinity? Now we can use the derivative. So infinity by infinity, right? You can take a derivative of first the numerator and denominator, right? Let's take a derivative with respect to t. So the derivative of this one, it is ft basically, right? The derivative of this guy is s e minus t. Okay, we take a derivative of a numerator and denominator. Okay, that's when we have infinity divided by infinity. This is if f tau d tau goes to infinity as t go to infinity. Okay, now this guy, typically this is a finite because it only talks about a value, right, at a certain point. Okay, so this guy still goes to infinity, right? So this one again goes to 0. That's why this term will be gone, because this guy, when t is going to infinity, is 0. When t is 0, it's still 0. It's 0 minus 0, so it's still 0. That term is gone. So we only have this term left. Remember, we still have 1 minus 1 over s, and we still have a minus sign. Don't forget our minus sign over here. So this minus sign will cancel out. So I have 1 over s times fs, because this guy is just definition of the Laplace transform ft. Okay, that's why we come to this conclusion. The Laplace transform integration of 0 to t f tau d tau is just equal to fs over s. Okay, so this is the last part we're going to talk about today. Is called derivative of ft. But the property says the derivative of ft is equal to s times fs minus f0. So this f0 is the here, initial value of ft, your original function. Even if it's a derivative, it's not the initial value of f dot t. Okay, it's ft. Okay, don't include the derivative over here. Okay, let's talk about why that's the case. Okay, if I take a linear, let's still use the definition because I don't have an original property. I cannot use the original property to analyze this. Okay, so let's take a look at this property using the definition. So the Laplace transform is given by integration from 0 to infinity e minus t times f dot t. Now this time, let's move this one ft to the right hand side. This is pretty simple because dft is just equal to f dot t times dt. Okay, because you can move this one to the left. You have dft over dt f dot t. That's true. Okay. Now I still do integration by part. Is e minus st times ft, t infinity, and evaluate t is infinity and t is 0. Okay, and then I swap the two. Is negative 0 infinity ft de minus st. Okay. Now this guy, okay, again, so when the limit t goes to infinity, e minus t ft, which is equal to limit t goes to infinity, ft over est. Okay, this guy, again, this guy will be equal to 0. Okay, so this is gone. When t is 0, so we replace t by 0, so e minus s times 0 is still 0. E minus 0 is gives 1, so 1 times f, remember still replace t by 0, so 1 times f0, yes, we have a 1 f0. Don't forget there's a minus sign because this is equal to the limit of t go to infinity, e minus st ft minus es minus 0 times f0, so they have the negative sign over here. And still minus again, 0 to infinity, so this guy is d of e minus t is this d e minus t is, use a chain rule, is minus times est minus t dt. Okay, that's why we have it here, and put ft over here again. So this one is, so I keep that minus f0 here again. So the minus and minus will cancel out, so I have plus. They move the s outside. The reason we can move s out because you English over t, not over s, so s is a constant, so move the s out. English from 0 to infinity ft e minus t. Again, this is just a definition of the Laplace transform of ft, which is just fs. So this is s times fs minus f0. Okay, so I guess I'm going to stop over here, and I'm going to talk some more property for Laplace transform in the next lecture.